1.5.3 Phase change and latent heat. So far, we have discussed heat transfers that cause temperature change. However, in a phase transition, heat transfer does not cause any temperature change. For an example of phase changes, consider the addition of heat to a sample of ice at -20 degrees Celsius, figure 1.15, and atmospheric pressure. The temperature of the ice rises linearly, absorbing heat at a constant rate of 2090 joules per kilogram, degrees Celsius until it reaches 0 degrees Celsius. Once at this temperature, the ice begins to melt and continues until it has all melted, absorbing 333 kilojoules per kilogram of heat. The temperature remains constant at 0 degrees Celsius during this phase change. Once all the ice has melted, the temperature of the liquid water rises, absorbing heat at a new constant rate of 4,186 joules per kilogram, degrees Celsius. At 100 degrees Celsius, the water begins to boil. The temperature again remains constant during this phase change while the water absorbs 2,256 kilojoules per kilogram of heat and turns into steam. When all the liquid has become steam, the temperature rises again, absorbing heat at a rate of 2020 joules per kilogram, degrees Celsius. If we started with steam and cooled it to make it condense into liquid water and freeze into ice, the process would exactly reverse, with the temperature again constant during each phase transition. Figure 1.15. Delta Q over M kilojoules per kilogram. T degrees Celsius. Ice. Ice plus water. Water. Water plus steam. Figure 1.15. Temperature versus heat. The system is constructed so that no vapor evaporates while ice warms to become liquid water, and so that, when vaporization occurs, the vapor remains in the system. The long stretches of constant temperatures at 0 degrees Celsius and 100 degrees Celsius reflect the large amounts of heat needed to cause melting and vaporization, respectively. Where does the heat added during melting or boiling go, considering that the temperature does not change until the transition is complete? Energy is required to melt a solid, because the attractive forces between the molecules in the solid must be broken apart, so that in the liquid, the molecules can move around at comparable kinetic energies. Thus, there is no rise in temperature. Energy is needed to vaporize a liquid for similar reasons. Conversely, work is done by attractive forces when molecules are brought together during freezing and condensation. That energy must be transferred out of the system, usually in the form of heat, to allow the molecules to stay together, figure 1.18. Thus, condensation occurs in association with cold objects, the glass in figure 1.16, for example. Figure 1.16. Condensation forms on this glass of iced tea because the temperature of the nearby air is reduced. The air cannot hold as much water as it did at room temperature, so water condenses. Energy is released when the water condenses, speeding the melting of the ice in the glass. Credit: Jenny Downing. The energy released when a liquid freezes is used by orange growers when the temperature approaches 0 degrees Celsius. Growers spray water on the trees so that the water freezes and heat is released to the growing oranges. This prevents the temperature inside the orange from dropping below freezing, which would damage the fruit, figure 1.17. Figure 1.17. The ice on these trees released large amounts of energy when it froze, helping to prevent the temperature of the trees from dropping below 0 degrees Celsius. Water is intentionally sprayed on orchards to help prevent hard frosts. Credit: Hermann Hammer. The energy involved in a phase change depends on the number of bonds or force pairs and their strength. The number of bonds is proportional to the number of molecules and thus to the mass of the sample. The energy per unit mass required to change a substance from the solid phase to the liquid phase, or released when the substance changes from liquid to solid, is known as the heat of fusion. The energy per unit mass required to change a substance from the liquid phase to the vapor phase is known as the heat of vaporization. The strength of the forces depends on the type of molecules. The heat Q absorbed or released in a phase change in a sample of mass, m, is given by Q equals m LF melting, freezing. 1.7 Q equals M LV, vaporization, condensation. 1.8 Where the latent heat of fusion LF and latent heat of vaporization LV are material constants that are determined experimentally. Latent heats are also called latent heat coefficients and heats of transformation. These constants are latent or hidden because in phase changes, energy enters or leaves a system without causing a temperature change in the system, so in effect, the energy is hidden. Figure 1.18. 1. Solid. Limits of motion. Energy input. Melt. Liquid. Energy input. Evaporate. Gas. 2. Gas. Energy output. Condense. Liquid. Energy output. Freeze. Solid. Figure 1.18. A. Energy is required to partially overcome the attractive forces, modeled as springs, between molecules in a solid to form a liquid. That same energy must be removed from the liquid for freezing to take place. B. Molecules become separated by large distances when going from liquid to vapor, requiring significant energy to completely overcome molecular attraction. The same energy must be removed from the vapor for condensation to take place. Table 1.4 lists representative values of LF and LV in kilojoules per kilogram, together with melting and boiling points. Note that in general, LV is greater than LF. The table shows that the amounts of energy involved in phase changes can easily be comparable to or greater than those involved in temperature changes, as figure 1.15 and the accompanying discussion also showed. Table 1.4. Substance. Latent heat of fusion, LF. Melting point, degrees Celsius. Kilojoules per kilogram. Kilocalorie per kilogram. Latent heat of vaporization, LV. Boiling point, degrees Celsius. Kilojoules per kilogram. Kilocalorie per kilogram. 1. Helium. 2. Melting point, negative 272.2 degrees Celsius, 0.95 K. 5.23 kilojoules per kilogram, or 1.25 kilocalorie per kilogram. Boiling point, negative 268.9 degrees Celsius, 4.2 K. 20.9 kilojoules per kilogram, or 4.99 kilocalorie per kilogram. 2. Hydrogen. Melting point, negative 259.3 degrees Celsius, 13.9 K. 58.6 kilojoules per kilogram, or 14 kilocalorie per kilogram. Boiling point, negative 252.9 degrees Celsius, 20.2 K. 452 kilojoules per kilogram, or 108 kilocalorie per kilogram. 3. Nitrogen. Melting point, negative 210.0, 63.2 K. 25.5 kilojoules per kilogram, or 6.09 kilocalorie per kilogram. Boiling point, negative 195.8 degrees Celsius, 77.4 K. 201 kilojoules per kilogram, or 48 kilocalorie per kilogram. 4. Oxygen. Melting point, negative 218.8 degrees Celsius, 54.4 K. 13.8 kilojoules per kilogram, or 3.3 kilocalorie per kilogram. Boiling point, negative 183.0 degrees Celsius, 90.2 K. 213 kilojoules per kilogram, or 50.9 kilocalorie per kilogram. 5. Ethanol. Melting point, negative 114 degrees Celsius. 104 kilojoules per kilogram, or 24.9 kilocalorie per kilogram. Boiling point, 78.3 degrees Celsius. 854 kilojoules per kilogram, or 204 kilocalorie per kilogram. 6. Ammonia. Melting point, negative 75 degrees Celsius. 332 kilojoules per kilogram, or 79.3 kilocalorie per kilogram. Boiling point, negative 33.4 degrees Celsius. 1370 kilojoules per kilogram, or 327 kilocalorie per kilogram. 7. Mercury, melting point, negative 38.9 degrees Celsius. 11.8 kilojoules per kilogram, or 2.82 kilocalorie per kilogram. Boiling point, 357 degrees Celsius. 272 kilojoules per kilogram, or 65 kilocalorie per kilogram. 8. Water, melting point, 0 degrees Celsius. 334 kilojoules per kilogram, or 79.8 kilocalorie per kilogram. Boiling point, 100 degrees Celsius. 2256 kilojoules per kilogram, 3, or 539 kilocalorie per kilogram, 4. 9. Sulfur, melting point, 119 degrees Celsius. 38.1 kilojoules per kilogram, or 9.1 kilocalorie per kilogram. Boiling point, 444.6 degrees Celsius. 326 kilojoules per kilogram, or 77.9 kilocalorie per kilogram. 10. Lead, melting point, 327 degrees Celsius. 24.5 kilojoules per kilogram, or 5.85 kilocalorie per kilogram. 871 kilojoules per kilogram, or 208 kilocalorie per kilogram. 11. Antimony, melting point, 631 degrees Celsius. 165 kilojoules per kilogram, or 39.4 kilocalorie per kilogram. Boiling point, 1440 degrees Celsius. 561 kilojoules per kilogram, or 134 kilocalorie per kilogram. 12. Aluminum, melting point, 660 degrees Celsius. 380 kilojoules per kilogram, or 90 kilocalorie per kilogram. Boiling point, 2450 degrees Celsius. 11400 kilojoules per kilogram, or 2720 kilocalorie per kilogram. 13. Silver, melting point, 961 degrees Celsius. 88.3 kilojoules per kilogram, or 21.1 kilocalorie per kilogram. Boiling point, 2193 degrees Celsius. 2336 kilojoules per kilogram, or 558 kilocalorie per kilogram. 14. Gold, melting point, 1063 degrees Celsius. 64.5 kilojoules per kilogram, or 15.4 kilocalorie per kilogram. Boiling point, 2660 degrees Celsius. 1578 kilojoules per kilogram, or 377 kilocalorie per kilogram. 15. Copper, melting point, 1083 degrees Celsius. 134 kilojoules per kilogram, or 32 kilocalorie per kilogram. Boiling point, 2595 degrees Celsius. 5069 kilojoules per kilogram, or 1211 kilocalorie per kilogram. 16. Uranium, melting point, 1133 degrees Celsius. 84 kilojoules per kilogram, or 20 kilocalorie per kilogram. Boiling point, 3900 degrees Celsius. 1900 kilojoules per kilogram, or 454 kilocalorie per kilogram. 17. Tungsten, melting point, 3410 degrees Celsius. 184 kilojoules per kilogram, or 44 kilocalorie per kilogram. Boiling point, 5900 degrees Celsius. 4810 kilojoules per kilogram, or 1150 kilocalorie per kilogram. Table 1.4. Heats of fusion and vaporization. 1. Values quoted at the normal melting and boiling temperatures at standard atmospheric pressure, 1 atmosphere. 2. Helium has no solid phase at atmospheric pressure. The melting point given is at a pressure of 2.5 megapascals. 3. At 37.0 degrees Celsius, body temperature, the heat of vaporization LV for water is 2430 kilojoules per kilogram or 580 kilocalorie per kilogram. 4. At 37.0 degrees Celsius, Body temperature, the heat of vaporization, LV for water is 2,430 kilojoules per kilogram or 580 kilocalorie per kilogram. Phase changes can have a strong stabilizing effect on temperatures that are not near the melting and boiling points, since evaporation and condensation occur even at temperatures below the boiling point. For example, air temperatures in humid climates rarely go above approximately 38.0 degrees Celsius because most heat transfer goes into evaporating water into the air. Similarly, temperatures in humid weather rarely fall below the dew point, the temperature where condensation occurs given the concentration of water vapor in the air, because so much heat is released when water vapor condenses. More energy is required to evaporate water below the boiling point than at the boiling point, because the kinetic energy of water molecules at temperatures below 100 degrees Celsius is less than that at 100 degrees Celsius, so less energy is available from random thermal motions. For example, at body temperature, evaporation of sweat from the skin requires a heat input of 2,428 kilojoules per kilogram, which is about 10% higher than the latent heat of vaporization at 100 degrees Celsius. This heat comes from the skin, and this evaporative cooling effect of sweating helps reduce the body temperature in hot weather. However, high humidity inhibits evaporation, so that body temperature might rise, while unevaporated sweat might be left on your brow. Example 1.9. Calculating final temperature from phase change. 3 ice cubes are used to chill a soda at 20 degrees Celsius with mass, m, soda, equals 0.25 kilogram. The ice is at 0 degrees Celsius and each ice cube has a mass of 6.0 gram. Assume that the soda is kept in a foam container so that heat loss can be ignored and that the soda has the same specific heat as water. Find the final temperature when all ice has melted. Strategy. The ice cubes are at the melting temperature of 0 degrees Celsius. Heat is transferred from the soda to the ice for melting. Melting yields water at 0 degrees Celsius, so more heat is transferred from the soda to this water until the water plus soda system reaches thermal equilibrium. The heat transferred to the ice is Q, ice, equals M, ice, LF, plus M, ice, C, W, open parenthesis, TF, minus 0 degrees Celsius, closed parenthesis. The heat given off by the soda is Q, soda, equals M, soda, C, W, open parenthesis, TF, minus 20 degrees Celsius, closed parenthesis. Since no heat is lost, Q ice equals negative Q soda, as in example 1.7, so that M, ice, LF, plus M, ice, C, W, open parenthesis, TF, minus 0 degrees Celsius, equals negative M, soda, C, W, open parenthesis, TF, minus 20 degrees Celsius, closed parenthesis. Solve for the unknown quantity TF. TF equals M, soda, C, W, open parenthesis, 20 degrees Celsius, closed parenthesis, minus M, ice, LF, divided by, open parenthesis, M, soda, plus M, ice, closed parenthesis, C, W. Solution. First we identify the known quantities. The mass of ice is M, ice, equals 3, multiplied by 6.0 gram, equals 0.018 kilogram, and the mass of soda is M, soda, equals 0.25 kilogram. Then we calculate the final temperature. TF equals 20,930 joules, minus 6,012 joules, divided by 1,122 joules per degree Celsius, equals 13 degrees Celsius. Significance. This example illustrates the large energies involved during a phase change. The mass of ice is about 7% of the mass of the soda but leads to a noticeable change in the temperature of the soda. Although we assumed that the ice was at the freezing temperature, this is unrealistic for ice straight out of a freezer. The typical temperature is negative 6 degrees Celsius. However, this correction makes no significant change from the result we found. Can you explain why? Like solid-liquid and liquid-vapor transitions, direct solid-vapor transitions or sublimations involve heat. The energy transferred is given by the equation Q equals m Ls, where Ls is the heat of sublimation, analogous to Lf and Lv. The heat of sublimation at a given temperature is equal to the heat of fusion, plus the heat of vaporization at that temperature. We can now calculate any number of effects related to temperature and phase change. In each case, it is necessary to identify which temperature and phase changes are taking place. Keep in mind that heat transfer and work can cause both temperature and phase changes. A. Problem-solving strategy. The effects of heat transfer. 1. Examine the situation to determine that there is a change in the temperature or phase. Is there heat transfer into or out of the system? When it is not obvious whether a phase change occurs or not, you may wish to first solve the problem as if there were no phase changes, and examine the temperature change obtained. If it is sufficient to take you past a boiling or melting point, you should then go back and do the problem in steps: temperature change, phase change, subsequent temperature change, and so on. 2. Identify and list all objects that change temperature or phase. 3. Identify exactly what needs to be determined in the problem. Identify the unknowns. A written list is useful. 4. Make a list of what is given or what can be inferred from the problem as stated. Identify the knowns. If there is a temperature change, the transferred heat depends on the specific heat of the substance, heat transfer, specific heat, and calorimetry. And if there is a phase change, the transferred heat depends on the latent heat of the substance. Table 1.4. 5. Solve the appropriate equation for the quantity to be determined, the unknown. 6. Substitute the knowns along with their units into the appropriate equation and obtain numerical solutions complete with units. You may need to do this in steps if there is more than one state to the process, such as a temperature change followed by a phase change. However, in a calorimetry problem, each step corresponds to a term in the single equation, Q hot plus Q cold equals 0. 7. Check the answer to see if it is reasonable. Does it make sense? As an example, be certain that any temperature change does not also cause a phase change that you have not taken into account. 1.5. Check your understanding. Why does snow often remain even when daytime temperatures are higher than the freezing temperature?